So question number 17. The question is this: the power radiated by a black body is P and it radiates maximum energy around the wavelength lambda naught. If the temperature of the black body is now changed so that it radiates maximum energy around a wavelength 3 lambda naught by 4, the power radiated by it will increase by a factor of, first of all, power radiated. Power radiated directly proportional to T to the power 4, temperature to the power 4. So as it is given, so from Wien's displacement law, lambda maximum into T is your constant. So if initial temperature is T, at that time lambda maximum your T. Initial temperature is T. Then maximum power from lambda. Then the power maximum corresponding to wavelength lambda. Now, when wavelength maximum is your 3 lambda naught by 4, then temperature by relation lambda 1 T1 is equal to lambda 2 T2. Lambda 1 lambda naught T, 3 lambda naught by 4 into T, T2. So T2 will be here 4 by 3 T. It means temperature now changes 4 by 3 times initial temperature. So power radiated. So power radiated becomes 4 by 3 2 to the power 4. And 4 by 3 to the power 4 is your, that is your 256 by 81 times initial power P naught. So that factor changes your 256 by 81. Correct answer, your option number 4 is the correct option. Question number 18. The question is this: 3 identical rods A, B, C are placed end to end. A temperature difference is maintained between the free ends of A and C. The thermal conductivity of B is thrice that of C and half of that of A. The effective thermal conductivity of the system will be, let K is the thermal conductivity of the rod A. First option Ka by 3, second option 3Ka, third option 2Ka, and the fourth option 2 by 3 Ka. Now, as per the given information, there are 3 rods A, B and C. These 3 rods kept side by side, and the temperature difference is maintained at the free ends of A and C. Okay, let this temperature difference here theta 1 and theta 2. And thermal conductivity of A is given here Ka, and all are the identical rods here, but they are dimensionally identical. And thermal conductivity of rod B is thrice that of C, the Kb, 3 of Kc, as well as thermal conductivity of B is thrice that of C and half of that of A, Ka by 2. So Kb is equal to Ka by 2. Kb is equal to your Ka by 2 and Kc is equal to Ka by 6. So they are asking the effective thermal conductivity. So H, total heat is your, that is K effective, A theta 1 minus theta 2 by L 3L. 3L is the total length, we can say, L, L and L. Same thing we can do from between these two. Let the temperature here your T1 and here temperature your T2. Same thing we can write here. That H is also equal to theta 1 minus T1 into K A area by L. In that manner we can write this also. Similarly, this is also equal to this and this also equal to this. So H is your Ka A theta 1 minus T1 by L equal to your Kb A T1 minus T2 by L, that is equal to your Kca T2 minus theta 2 by L. And this value we can substitute in any of the expression. See, to H. From here we can put the value of T1, T2 and T3. See, this is your equation number 2. From equation first, K effective is equal to your H 3LH by area theta 1 minus theta 2. We would like to find this value here, theta 1 minus theta 2, by substituting this relation. See, A by L cancel. From equation 2 we can write Ka theta 1 minus T1 is equal to Kb T1 minus T2, and see, Ka theta 1 minus T1 by L is equal to your H. So T1 is equal to your, or theta 1 minus T1 is equal to HL by Ka. Similarly, from here, so T1 is equal to theta 1 minus HL by Ka, and T2 is equal to your theta 2 plus HL by K C. Now substituting these value in the third, now from second and third, we will get K effective. K effective is equal to your Ka by 3. So our correct answer is your option number 1 is the correct option. Question number 19. It takes 20 minutes to cool a liquid from 61 degrees Celsius to 59 degrees Celsius. If room temperature is 30 degrees Celsius, then time taken in cooling from 51 degrees Celsius to 49 degrees Celsius. The option 1 is 10 minutes, option 2 is 11 minutes, option 3 13 minutes, and option 4 15 minutes. See, according to Newton's law of cooling, d theta by dt is minus k theta minus theta naught. In the first case, change in temperature your 59 degree from 61, that is your 2, and it takes total time is your 10 minutes. minus K, 59 this is your 60 minus theta naught surrounding temperature your 30. So 1 by 5 is equal to your minus 30 K, first equation. In second case, change in temperature your 51 to 49, 2 by T minus K, 50 minus 30. So from first and second, 1 and 2, T by 10 is equal to your 30 by 20 or 3 by 2. So T is your 15 minute. So correct option your option number 4. Question number 20. In this question here, the plot of intensity versus wavelength for 3 black body at temperatures T1, T2, T3 has been shown. Their temperatures are such that the first T1 greater than T2 greater than T3, in the second T1 greater than T3 greater than T2, and third is T2 greater than T3 greater than T1, and the fourth is T3 greater than T2 greater than T1. Okay, now see here. As per the graph, this is your intensity versus, and these type of some graphs are given here. This is at temperature T1, this is T3, this is your T2. So what has been found according to Wien's displacement method, as the temperature your increases, the lambda into T is your constant. This is your Wien's displacement law. So as temperature increases, the wavelength corresponding to maximum intensity or decreases. So here this T1 has minimum wavelength. The wavelength for this minimum, temperature will be maximum. So T1 will be maximum, then T3, then T2. So our correct option is your option number 2 is the correct option. Question number 21. In a steady state of thermal conduction, temperature of end A and B are of a 20 cm long rod or 100 degrees Celsius and 0 degrees Celsius respectively. What will be the temperature of the rod at a point at a distance of 6 cm from the end A of the rod? First option minus 30 degrees Celsius, second option 70 degrees Celsius, third option 5 degrees Celsius, fourth option 50 degrees Celsius. Now see how to do this problem here. See, this is the rod and the length of the rod is given 20 centimeter and one let at your 100 degrees Celsius, another end at 10 degrees Celsius. And they are asking the temperature at 0.6 centimeter. See, it can be said just like two rods having same thermal conductivity. Length is your 6 centimeter and this is your 14 centimeter. 100, theta and 0 degrees Celsius. See, if we are looking the resistance, as we know R is equal to L by Ka. This have length 6 by Ka. Let this your R1. So R2 your 14 by Ka. Total R is your R1 plus R2. That is your 20 by Ka. First heat. Heat H is equal to your 100 minus this, 100 minus 0 by R, 20 by K. Same thing here, 100 minus theta by 6 by Ka. So from here we can have 5 is equal to 100 by 6, 100 minus theta by 6. So 100 minus theta is your 30. The theta is your 70 degrees Celsius. So our answer is the option 2 is the correct option, that is 70 degree Celsius. Question number 22. In a 10 meter deep lake, the bottom is at a constant temperature of 4 degrees Celsius and the air temperature is constant at minus 4 degrees Celsius. The thermal conductivity of ice is 3 times that of water. Neglecting the expansion of water on freezing, the maximum thickness of ice will be first year 7.5 meter, second 6 meter, third is 5 meter, fourth is 2.5 meter. See the answer here. It is given, let this your deep lake and the temperature at the, it is given 4 degrees Celsius and here temperature your is air. This is your water and some with ice. This is let your ice. This is ice and let this your L. Total is your 10 meter. So now they are asking what is the width of the ice. So what will happen here? This water here 4 degrees Celsius and here air is your minus 4 degrees Celsius. So rate of flow of heat, whatever the rate of heat is flowing here from higher temperature to, and this one more thing here there, it is given the conductivity. Neglecting the expansion of water, the maximum thickness of ice will be. Conductivity of ice, thermal conductivity of ice is 3 times that of. So let thermal conductivity of water is your K. So thermal conductivity of ice is your 3K. It is given 10 meter deep lake and the bottom of the lake have temperature 4 degrees Celsius and air temperature your minus 4 degrees Celsius. Thermal conductivity of ice 3 times the thermal conductivity of water. Let the thermal conductivity of water is K, ice is your 3K. Now, this is the interface between the water and ice. So this temperature must be 0 degrees Celsius. So whatever the heat is flowing from this to this, same amount of heat flow from here to here, then the thermal equilibrium will be there. So rate of heat flow from here, H, that is your K, A, difference of temperature 4 minus 0 by this width 10 minus L, that is equal to your rate of heat flow from here, thermal conductivity, this is 3K, A, temperature difference here 0 to minus 4, 0 to minus 4 becomes plus 4 by this your L. Now we can simplify this, Ka can cancel, 4 and 4 also cancel, 1 by 10 minus L is equal to your 3 by L. So L will be your 7.5 meter. So width of the ice, this is your ice width of the ice 7.5 meter. So our correct option is your option number 1. Question number 23. It is given as 3 discs A, B, C having radii 2 meter, 4 meter and 6 meter respectively are coated with carbon black on their outer surface. The wavelength corresponding to maximum intensity are 300 nanometer, 400 nanometer and 500 nanometer respectively. The power radiated by them are Q1, QA, QB, QC respectively. Then first option QA is maximum, second option QB is maximum, third option QC is maximum, fourth option QA is equal to QB is equal to QC. So power radiated is directly related to area of surface area and temperature of the disk. Power radiated is directly proportional to T to the power 4 into area. According to Wien's displacement law, lambda into T is your constant. So T is proportional to 1 by lambda. So power radiated can be said as 1 by lambda to the power 4 into area. Now, same thing if we are writing for QA. QA is your some constant. Area of the first disk is her radius your 2 meter. So area will be your pi into 2 square by lambda to the power 4. Lambda for this your 300 to the power 4. So this can be said as some another constant K dash 4 by 81. Similarly QB, K pi, radius of that is your 4 meter. So 4 square, and the wavelength corresponding to maximum radiation your 400. So 400 to the power 4. This can be said as K another constant 16 by 256. Now QC if we are calculating, K pi, radius of that disk is your 6 meter, 6 square, and wavelength corresponding to maximum radiation is given 500. This is your K dash 36 by 625. Now when we are simplifying this, so what we are getting, QB is your maximum. See, this is your 1 by 20 around, and this is your more than that, and then this is your further more than this. So here out of these, QB is your maximum, or option number 2 is the correct option. Question number 24. A body cools in a surrounding which is at a constant temperature of theta naught. Assume that it obeys Newton's law of cooling. Its temperature theta is plotted against time t. Tangent are drawn to the curve at point P, that your theta is equal to theta 2 and theta is equal to theta 1. So now these tangent meets the time axis at an angle phi 1 and phi 2 as shown. So which one are the correct option? Tan phi 2 by tan phi 1 is equal to theta 1 minus theta naught by theta 2 minus theta naught. Similarly, second option, tan phi 2 by tan phi 1 is equal to your theta 2 minus theta naught by theta 2 minus theta naught. And third option, tan phi 1 by tan phi 2 is theta 1 by theta 2. And the fourth option, tan phi 1 by tan phi 2 is equal to theta 2 by theta 1. Now see the solution here. As per the diagram mentioned, temperature of a body changes with time as like this. Here there are two tangent has been drawn. This is the tangent at temperature theta 1, theta 2, and here a tangent at temperature theta 1, this angle your phi 1, and this is your phi 2. According to Newton's law of cooling, d theta by dt is minus k theta minus theta naught. So this d theta by dt give you the slope. So here we can write here tan phi 1 is equal to your theta 1 minus theta naught. Similarly, tan phi 2 is equal to your theta 2 minus theta naught. So our result tan phi 2 by tan phi 1. Tan phi 2 by tan phi 1 is your theta 2 minus theta naught by theta 1 minus theta naught. So correct option your option number 2. Question number 25. A sphere and a cube of same material and same total surface area are placed in the same evacuated space turn by turn after they are heated to the same temperature. Find the ratio of their initial rate of cooling in the enclosure. So first thing is that surface area of the sphere. This is the sphere, let have radius r, and this is the cube, have let side your L. Surface area is the same, and 4 pi r square is equal to your 6 L square. So we can say the mass. Mass of sphere ms, mass of cube your mc. Mass of sphere, it is given sphere same material. The mass of sphere is your rho into 4 by 3 pi r cube, and mass of cube rho into L cube. L cube value we would like to write here from here. L is equal to your 2 pi r square by 3. This is 2 pi r square by 3 power 1 by 2. So this is the rho. So this further we can say mc is equal to your rho, and this is rho into r cube into 2 pi by 3 to the power 2, and mass of the sphere rho into, so that can be converted in the other form. So now find the ratio of their initial rate of cooling. The initial rate of cooling that we have to calculate. The C. Initial rate of cooling if we require. So as we know, d theta by dt is our minus k theta minus theta naught. So that depends on the value of k here. And how it has come, see. As we know, q is equal to ms theta, dq by dt is your ms d theta by dt, and dq by dt according to, by using the Stephen's law, what we found, d theta by dt, rate of cooling your inversely proportional to mass. See, rate of cooling is inversely proportional to mass. So rate of cooling of sphere versus cube. Sphere by cube is equal to your mass of cube by mass of sphere, and mass of cube we can write like this: rho r cube 2 pi by 3 to the power 3 by 2 by rho r cube 4 pi by 3. So now we can write like this: 2 pi by 3 root over 2 pi by 3. This is your 2 into 2 pi by 3. 1 2 pi by 3, 1 2 pi by 3 cancel. Now, this further we can say root over 2 pi by 12, root over pi by 6. So this is the correct option. So option number your 1 is the correct option. The main point is the rate of cooling is your inversely proportional to mass of the body. Question number 26. Two rods having thermal conductivity in the ratio of 5 by 3 and having equal length and equal cross section are joined face to face as shown. If temperature of free end of the first rod is 100 degrees Celsius and the free end of the second rod is 20 degrees Celsius, then calculate the temperature of the junction. First option 50 degrees Celsius, second option 70 degrees Celsius, third option 85 degrees Celsius, and the fourth option 100 degree Celsius. Now see, it is given there are two rods. Let this your one rod, this is your another rod, and these two rods have their thermal conductivity in the ratio 5:3, and K1 let your 5K and K2 your 3K, and having equal length and cross sectional area, and the free end of the first rod is 100 and the other 20 degree. 100 degrees Celsius, this is your 20 degrees Celsius. So the rate of flow of heat from here to here will be same, H, and this is also your H. H is equal to K A 100 minus theta by length L, also equal to K A theta minus 20 by L. Now we can simplify Ka by L cancel. So 500 minus 5 theta, 3 theta minus 60. 8 theta is 560. Theta is 70 degree Celsius. The temperature of the junction is your 70 degrees Celsius. So option is your second option is the correct option. This is the final answer.